Okay, so in this set of notes, we're going to talk about conditional probabilities and independence. And these are two highly related ideas, okay? So conditional probabilities and independence. Okay, so what is a conditional probability? All right, conditional probability is that I have two events. Let's say A is the event that I randomly select from uh, a population boy, and B is I randomly select a 11th grader, right? Okay, so what we want to do is we're going to say, I know B happened. Okay, so I'm given, another way of saying this is I'm given that B happened. Then I want to know what is the probability of A. So if I know this happened, then what is the probability of A happening? Okay, so another way of writing this is I could say, what is the probability of A given B? Or another shorthand way of writing this is the probability of A given B. Okay, so we're going to give an example to this in a second here, but I want to clear the screen so we get some space. And I'm going to first give you a formula that works for calculating this, and then we're going to show you like kind of intellectually why it works. Okay, so hold on. Let me clear the screen and we'll start there. All right, so we have this formula. We're going to say that the probability of A given B is equal to the probability of A and B, so you read that cap as and, over the probability of B. Okay, so what does this mean? What does this mean is pretty simple. It means that, so let's see, A was picking a boy, B was picking an 11th grader, right? All right, so let's say this is my population. I have 1, 2, 3, 4, 5, 6, 7, 8 boys, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 girls, right? So I have a total of my population of 18. 8 of them are boys, 10 of them are girls. Okay, so I have 2 ninth graders, I have 2 10th graders. Oops, that's not going to make sense. 2 10th graders. I have 3 11th graders, and I have 1 senior in the population. I have 2 nines. I have 3 10s. I have 1 11, and I have a whole bunch of seniors in the population here, right? So this is my population. Okay, so A given B. Okay, so I'm given B. I'm given that that the person that I'm selecting is an 11th grader. So that means I have picked one of these 3 people, or I've picked this one, because that's all the 11th graders, right? These 3 and this one. So that means, given that I've picked an 11th grader, given that I've picked one of those 4 people, what is the probability that it's a boy? Well, 3 out of 4 of those are boys, right? So this should be the probability of getting a boy, given that I have an 11th grader. Okay, how does that line up with my formula here, right? So I'm saying that the probability of getting a boy, given that I have an 11th grader, is equal to the probability of getting a boy and an 11th grader, right? So 11th grade boys, there's 3 of those, right? And that's out of everybody now, right? The probability of getting 3 of those out of, well, let's see, there were 1, 2, 3, 4, 5, 6, 7, 8 plus 2, 4, 6, 8, 10, 12, right? So 3 out of 12 were both boys and 11th graders, right? The denominator here is the probability of getting a boy, right? So just the probability of getting a boy out of the hole. Well, 1, 2, 3, 4, 5, 6, 7, 8 out of 12. 12. 8 out of 12, right? And we know that to divide is to multiply by a reciprocal. So lo and behold, the 12s cancel out and I'm left with 3/8. So my handy dandy little formula here says the same thing as our intuition. Yay, it's good when math lines up with reality. Okay, so this is what it means to calculate a conditional probability, right? Given that you're in a group, what's the probability that you have a certain characteristic, right? Given that I'm in the group of 11th graders, what's the probability that I have the characteristic of being a boy? Okay, so this leads us to our next step in the game. Okay, so 2 events are independent. 2 events are independent if the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. So the given event has no effect on the probability. Okay? So let's think about what this means. Let's take something that's like clearly independent. I have a coin that I'm going to toss, and it can be heads or tails. And I have a die that I'm going to roll, and it can come out as 1 through 6. So I want to be the probability. I want to know if getting a heads and rolling a 6 are independent. Right? Well, the probability of getting heads on the coin, given that I rolled a 6, well, that's still 1/2, right? The coin toss did not affect. It was not affected by the die roll. The probability of getting a 6, given that you had a heads on the coin toss, is still 1 in 6, right? And this happens to be equal to the probability of getting heads all the time, and this happens to be equal to the probability of getting the 6 all the time. So I can say that the probability of heads given a 6 is equal to the probability of heads, and the probability of 6 given heads is also the probability of 6, which means that these events, the coin toss landing on heads and the die roll landing on 6, are in fact independent. Okay, so this is going to matter when I start calculating intersections. Okay, so let's start looking at the probability of an intersection. So the big question here is just like, how do I calculate the probability of the intersection of 2 events? Now, we said that you could calculate the union of 2 events using the addition rule. We're going to calculate the intersection of the 2 events using what we're going to call a multiplication rule. So I'll put that up here. Now, you actually already know this rule from something we did earlier. Earlier in this lesson, we said that the probability of A given B is equal to the probability of A intersect B over the probability of B. Okay, this means I know how to calculate this, because if I cross multiply my way out of this, I get that the probability of A given B is going to be the product of these things. Is the probability, sorry, of A and B is going to be the probability of A given B times the probability of B, which is awesome. Okay, so this is my multiplication rule for calculating an intersection, right? So you can take this and multiply by the conditional probability and then by this, right? So let's see. If I have like the probability of getting heads, no, let's not do that. Let's go, because that's not, those are independent. Um, let's try this. Um, let's say I have, um, I'll use my boy girl example again. Or maybe we could do this. Let's make 3 squares and 4 circles. 1, 2, 3, 4. And we're going to make 1 square green, 2 circles green. We will make 1 square red. We'll make 1 circle red. And we will make 1 square blue. And we'll make 1 circle blue. Okay. So, let's make B be getting a circle, and let's make A be getting a green shape. Okay, so I want to know the probability of getting a circle and a shape that is both green and a circle. Okay, so I could calculate this using conditional probabilities, right? The probability of getting a green shape given that I have a circle. So given that I have a circle, I have 4 circles. Out of that is a green shape, so that's 1/2, right? 1/2 of the circles are green. So given that I have a circle, the probability of getting a green one is 1/2. Now what's the probability of getting a circle? Well, the probability of getting a circle is 2. There's 2 circles. Out of 1, 2, 3, 4, 5, 6, 7. 2 out of 7, right? So the 2's cancel out here, makes this 1/7. So the probability of landing something that is green. I'm sorry, that's not correct. Back that up. The probability of getting a circle is definitely not 2/7. The probability, so how many circles do we have? We have 4 circles, right? Out of 7 shapes. So the probability of getting a circle is 4/7. Ah, there we go. Fix your mistakes. So 2 goes into 4 2 times. The result is 2/7. Okay, and can we see this more clearly, like the probability of A and B, right? Well, all total in the set, there are 1, 2, 3, 4, 5, 6, 7 things, right? And the number of green circles is 2. So yes, these should be the same, right? So this says that this formula right here works, okay? So like, why do we care? Okay, because you might be given like this probability and might be given that probability. You need to find that one. These are kind of useful things. Okay, so this is like our basic multiplication where you find ands by multiplying the conditional probability by the condition, or by the given, right? So now, here's an interesting thing, and this is where like intersection comes into all of this. Okay, so we just said that the probability of A and B is equal to the probability of A given B times the probability of B. Before we said if A and B are independent, that the probability of A given B is equal to the probability of A, because the B has no effect, right? So that means in this equation here, if the things are independent, this is equal to that. So I can rewrite this as the probability of A and B is equal to the probability of A times the probability of B, which makes it like really easy, right? So independence allows me to just simply multiply the probability of the two events toward each other. So that's a special case of the multiplication rule, right? So I'm going to recap real quick because there's a couple formulas in this that you need to have. Okay, real quick, the formula for the conditional probability A given B is the probability of A and B over the probability of B, right? Independence means that the following two are true. The probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. Okay, so that's what happens when you have independence. From this, I can rearrange this and say that the probability of A and B is equal to the probability of A given B times the probability of B, right? And we're calling that the multiplication rule. And that rule gets simplified if A and B are independent. Then we can say that the probability of A and B is just simply the probability of A times the probability of B. And we're basically combining this rule with that statement, because then the probability of A given B is the probability of A. Put that in there and you drop down to this. So this is like a multiplication rule for independent events. All right, so there you go. There is conditional probabilities and independence in a nutshell.